Hello, ladies and gentlemen. This is Alice Zhang from Peking University, and I'm so glad to meet you again on iCANX stage. And today is our last day for our iCANX summit for this year. So we are so glad to have all the friends to join together. And today we are very nice to celebrate, for our iCANX summit. I review the process. Yeah, and the first day is Wednesday. We have, Professor Jagdish and Professor Hong Ping on the stage to deliver a plenary talk. And yesterday we have Professor Jagdish, we have Professor David Leahy, we have Professor Hill, we have Professor Li Hong Wang. Such a big show, last night for 4 hours. All this wonderful, excellent speech. Yeah, we are so proud to have all of them. So that's the second day for 4 plenary talks. So today is the last day. We have two plenary speakers here. First is Professor Jiandong Ding, was from Fudan University. Second is Chen was from MIT. So yeah, this was our last, the most important plenary talk for this iCANX summit. So yeah, let's get to the process. Welcome my colleague Fulan. Yeah, to introduce our, last speakers. Lan, are you ready?
Yes, thank you,
Please.
Alice. Good evening, everyone. I'm really delighted to present the first plenary talk of tonight from Professor Jiandong Ding of Fudan University. So let me introduce a little bit about Professor Ding. Dr. Jiandong Ding is a distinguished professor of biomaterials and polymer science at Fudan University and the director of State Key Laboratory of Molecular Energy of Polymers. Professor Ding is the leading scientist of a national research and development program about biomedical materials in China. He serves as the executive associate editor of the journal Regeneration Biomaterials. His group won the first place prize of natural science research from State Ministry of Education of China. He was the winner of Outstanding Young Scientist Scholar by NSF of China and also awarded the Science and Technology Prize in Young Science Chinese by the State Association for Science and Technology of China. His patent regarding medical hydrogels was awarded as gold medal in Inventions Geneva. And also Professor Ding has made significant impact on technology translation from bench to bedside. And in 2016, he was elected as Fellow of International Union of Societies of Biomaterial Science and Engineering for the development of cell-responsive biomaterials for tissue engineering, regenerative medicine, and drug delivery. So let's welcome Professor Ding to the stage to deliver his plenary talk on biomaterial microenvironment and tissue regeneration. Please, Professor Ding.
Thank you, Professor Fu, for your nice introduction. I would also like to thank Alice and all the scholars to organize such a wonderful platform, iCANX. I really like it, as soon as I was invited to enjoy in it as a panelist. Today, my topic is about biomaterial research. And this research is closely related to cell studies and tissue regeneration. My topic today could be roughly divided into 4 parts. First, I will give a brief introduction, what a microenvironment of tissue regeneration is. And then I will give some demonstration about the stiffness effects on cell differentiation and the nanocure surface chemistry to regulate the cell adhesion and differentiation. The last part is a story from a case from bench to bedside. Now I will give a brief introduction about the so-called microenvironment. The microenvironment of tissue regeneration can compose of the material-based microenvironment, tissue-based microenvironment, and a changed microenvironment along with material degradation and tissue growth. All of this lies in a very fundamental question about the cell and material interactions. Now, as the material-based microenvironment environment is concerned, it contains chemical composition, geometry and topography, charge effect, the stiffness and the biomechanics, which will be emphasized in my talk, and also about the spatial distribution of bioactive ligands. This is another emphasis on my talk tonight, and I think also the morning in some other countries, such as the eastern area of the United States. Well, cell exhibit different and complicated behaviors on the material surface, including cell adhesion, migration, proliferation, communication, and differentiation. My talk cannot cover all of this, but we will concern cell adhesion, migration, and differentiation. Among all of the cell events, cell adhesion is the first one and very important. I would like to emphasize that cell adhesion is a biological process. So it's quite different from a coating, just like a material in physics or chemistry. So cell adhesion is not merely cell attachment. Now, this is a schematic presentation of the so-called focal adhesion. Now, it is amazing that a lot of cells, if they were cultured on a plate, they can generate some focal adhesion plaques, like a swarm, you see. And the cell migration is complete along with the formation of new focal adhesion plaque and disruption of the old focal adhesion plaque. It is quite complicated. And although cell biologists have been devoted in this area for about a half century, it still has not been fully elucidated. And some pioneering scientists in the biomaterials, they put forward a strategy to fabricate some patterned surface. Such pattern with cell adhesion contrast. Some area can trigger the focal adhesion, but some other area is non-folding. By this way, some real science could be elucidated to some extent. And the representative team is a multidisciplinary team led by Professor George Whiteside in chemistry, Harvard University. He developed a lot of wonderful technique about a self-assembly modulator, and also another team led by Professor Donald Ingber in Harvard Medical School. However, in which ways is our work unique? So we have investigated the adhesion and the differentiation of cells on regular RGD patterns on PG hydrogel surfaces. We have prepared both micro patterns and nano patterns. We have examined both matrix stiffness and surface chemistry. We have revealed both cell cues and material cues. And tonight I will give just some examples. Now, here is a schematic presentation about how many factors influence the cells. So they include the cell cues and the material cues, or ECM cues. ECM means extracellular matrix. It is also a biomaterial, and also the soluble factors. So the pure biologist is most interested in the soluble factors. But tonight, my topic is about the cell-material interaction. So we will use the soluble factors, but we will rule out the interference of the soluble factors or keep exactly the same level of soluble factors. But for the cell-material interactions contained many cues, they are always decoupled with each other. It is really difficult to determine which cue really works on some event. So we need to decouple these cues by surface patterning. This is the main motivation of our fundamental research during the last score of years. Now I give some the introduction of the first part of the new input, our group, in cooperation with a German group. We established a material technique platform to fabricate RGD pattern on PG hydrogels. Before I were in cooperation with Professor Schwartz, my group have some technique for PG hydrogel, and his group has some technique for the RGD pattern, but on silicon. So our cooperation is aimed to establish a completely new technique and a very difficult technique platform to fabricate RGD patterns on PG hydrogels. So why RGD? RGD means arginine glycine aspartate. It's a sequence naturally existed in some extracellular matrix. It acts like a ligand, can be bioconjugated with its receptor, integrin. Integrin is a transmembrane protein, and the bioconjugation of RGD and integrin can trigger the subsequent biological responses. So the RGD is really very important for biomaterial modification. So why nano? The nano is a very smart term. Usually I avoid using this term unless it is absolutely necessary. Now I would like to cite a paper in Science. It's a paper for the structure biology. This paper can tell us what is the size of integrin. The size is about 10 nanometer. So we hypothesize that if we fix one nanodot, also about 10 nanometer on the solid substrate and link RGD, and then we culture cell on the substrate. So the RGD can spontaneously biconjugated with integrin. So by this way, we can use one nanodot to control one integrin. So we can use the nanodot array to control the spatial distribution of integrin. That's the underlying science. Then the why PEG hydrogel. PEG indicates polyethylene glycol. It is a famous polymer. So we are interested in PEG hydrogel because we realize that the Harvard technique to introduce PEG is just to use self-assembly monolayer. It cannot be very stable during the cell culture. But if we replace the self-assembly monolayer to the PEG hydrogel, it can persistently non-folding. Why persistent non-folding? Because we would like to use to examine the RGD effect. But the cell adhesion contains two parts. One is specific cell adhesion. The other is non-specific cell adhesion, just triggered by some adsorptor proteins. We must use the background to potently, persistently keep the non-folding, and then we can examine the well-control our cell experiment on a well-defined micropattern. And also another motivation is that the PEG hydrogel can be used to adjust the matrix stiffness. However, PEG is inert. You can chemically link RGD to PEG. Also, it is not easy, but it is extremely hard to keep the RGD on the PEG hydrogel in a regular way. Before my group joined in this field, no one can do like this. So my group has spent 6 years from the basic idea to the primary patterning on the hydrogel. We spent an additional few years from material improvement and cell studies. So we eventually obtained the pattern. This is not directed for clinical application, but aimed at a one-sentence statement on science, unambiguous. Now, what I would like to give a very brief idea is just the basic idea of our material technique. Because it is almost impossible to link an array, RGD array, directly to the PEG hydrogel. So we put forward a transfer lithography technique. We prepared the golden nanopattern on glass and used the immobilized linker to form a polymer, and then we transfer the pattern to the polymer. So how to generate the pattern? We employed the block polymer micelle lithography. Here is the amphiphilic block polymer. It can form the micelle in selective solvent and also encapsulate gold acid into the core. Using the dip coating, we can obtain the pattern of micelle, and then we use plasma treatment. The plasma treatment can remove the polymer template, and meanwhile to reduce the gold acid to gold. So by this way, we can generate the gold nanoarray. And here is a characteristic by the AFM. You can see from the height of the AFM scale, the size of the gold dot is a bit less than 10 nanometer. So it is what we would like to make. And also we synthesize the PEG hydrogel using a technique called PEG macromonomer. So initiated from the PEG with two hydroxyl end group, we use the acrylyl chloride to link the double bonds to both ends. And then we use the photopolymerization to cross-link the macromonomer to obtain the PEG hydrogel. Here is one of the early image of the gold nanoarray on the PEG hydrogel. And then we would like to change the gold array to the RGD array. And then we can culture cell. So the natural RGD is just a linear sequence, but stimulated by a German scientist, Professor Kurt Kessler. He is an organic chemist. He designed a cyclic RGD because by this way, the RGD is more stable and more efficient to bioconjugate it with integrin. So we also follow his synthesis to prepare the RGD peptide, and we linked to the gold nanodot. Here is a demonstration of the cell culture. You can see cell can adhere well on the nanopatent area, but it's really the background is non-folding. And besides the dip coating, you can see the very significant contrast of cell adhesion. This is a SEM image due to some shrinkage of the cell prior to the sample, during the sample preparation. You can see the cell adherent to the nanodot. So our technique is successful, not only in the chemistry and the physics, and also in cell, in the cell experiment. One of my students, graduate student, colored the cells and used his picture to join in the competition for the scientific art. So I always encouraged my students to enjoy scientific life from the art. So personally, I also liked this image very much. So I would like to give a summary of the first part. The Harvard University is characterized by soft printing plus self-assembly monolayer, and our technique is block polymer micellar lithography and transfer lithography. By this way, we can prepare for the first time the PEG hydrogel and the RGD nanopatent, the RGD nanoarray on the PEG hydrogel. So this is not directly to use in the human body, but it can be used to well-control the cell behaviors. So we would like to reveal some real science, okay? Now I would like to give a story about the complicated science revealed or determined or assisted and by our unique technique. So the new input our group is a deterministic experiment of the stiffness effect on stem cell differentiation based on our unique surface patterning technique. I'd like to mention two famous publications. This is really a milestone during the last half century in the cell biology, biomaterials, and regenerative medicine. In 2005, in a science paper, one paper is entitled Tissue Fill Cells, feel and the response to the stiffness of the substrate. And also in a Cell paper next year, and the first author with Adam Engler, and corresponding author with Dennis Disher from University of Pennsylvania, they wrote an article called Matrix Elasticity, Direct Stem Cell Lineage Specification. So it is really wonderful. They revealed that matrix stiffness is a physical signal. It's a physical signal to regulate a stem cell differentiation. So they became very famous. However, after a few years, some European groups led by Professor Watt and Professor Huck, they published another paper to argue the well-established viewpoint about the stiffness effect. The title is Extracellular Matrix Tethering Regulates Stem Cell Fate. So here is some sentence in their paper. Cell spreading and differentiation are unaffected by matrix stiffness. So they think that the so-called stiffness effect, just because when the Disher group changed the stiffness effect, they also changed the surface chemistry. And the different surface chemistry lead to the different protein adsorption from cell culture in serum. So that's the real reason. And then it's a big problem, of course. And after a few years, the older first author and now also a PI in California, UCSD, Adam Engler, he published an argued paper. And in his publication, he wrote, differentiation does not depend on tethering. So to be or not to be, that is a question addressed by Prince Hamlet. And now matrix stiffness or surface chemistry. That is question for researchers, scholars in the fields of biomaterials, cell biology, and regenerative biomaterials, and medicine all over the world. So we think that the key is that we should design a very strict experiment to well decouple the matrix stiffness effect and the potential surface chemistry effect. And our unique surface patterning technique can do such a very can real such a very tough task. Now here is the schematic presentation of our experimental procedure. We first use the block polymer mysolithography to obtain the gold nanoarray, and we transfer the gold nanoarray to the PG hydrogel, and we link RGD and then we culture cell. So here is a more brief schematic presentation. Because we transfer the already formed the golden nanoarray to the PG hydrogel, so we can control the surface chemistry. Another key factor is that our nanoarray was generated on the PG hydrogels, which is very potent to resist non-specific cell adhesion. By this way, the protein adsorption could be ruled out completely, and then we can well examine whether or not the matrix stiffness effect does work. So here is it's a fluorescence micrograph of the mesenchymal stem cells. According to our statistics, we did found more spreading and tension of mesenchymal stem cells. So our experiment confirmed the stiffness effect based on a deterministic experiment. So, however, it is only for cell adhesion. If one scientist would like to examine cell differentiation, it is much more challenging because the cell differentiation cannot be finished during one day. However, the protein in the cereal will highly probably adsorb on the surface. So an ideal surface should resist the non-specific protein adsorption for quite a few days. That is our materials. So here is a demonstration. We can see that the non-folding background could be kept for at least 1 week. That is sufficient to examine the cell differentiation. Now, here is the differentiation in the medium of the mixed medium of orthogenic and adaptogenic medium. And we did see the blue color indicates the orthogenic differentiation. The red color indicates adaptogenic differentiation. Our statistics indicated that matrix stiffness can regulate the both lineage conjugates. So we also give the preliminary interpretation because the stiff matrix could lead to more tension. So it is beneficial for orthogenic differentiation. And meanwhile, the soft matrix leads to less tension, I mean the intracellular tension, and then it is beneficial for adipogenesis. Now we confirmed the matrix stiffness using a deterministic experiment. And next, I will give some new finding about the nanocube. So the new input, our group, is that we found the nano spacing of RGD is a regulator of stem cell differentiation. No one realized this before we published our paper. Now, this is the basic idea. We would like to check the factors to influence stem cell differentiation. It could be influenced by matrix stiffness and also by surface damage. So because our unique technique can decouple these two factors, so we can examine stiffness effect under a given RGD array with the same RGD nano spacing and under the PG hydrogel. We can also examine the nano spacing effect on the same matrix. Okay. Now we again use the block polymer micelle nanolithography, prepare the golden nano array, and also link RGD. And we also non-folding to keep the background and non-folding. Now here is some experimental image about the nano array with a series of nano spacing. And also we cultured our cells on a series of nano pattern. We did found the effect of cell adhesion with the change of cell adhesion with the increase of cell with increase of RGD nano spacing. And we also no, I would like to emphasize that the nano spacing effect on cell adhesion was first reported by Professor Joachim Schwarz. However, for the nano spacing effect on the cell differentiation, that was first reported by our group. And this is much more difficult because to examine the cell differentiation, you must keep the background non-folding for quite a long time. But anyway, we found that both the orthogenic differentiation and adaptogenic differentiation can be adjusted by the RGD nanospacing. What is more interesting is that with the increased RGD nanospacing, although the cell spreading area will be decreased. And before our study, Professor Christopher Chen in the United States from Johns Hopkins, he has reported that with more cell spreading, it is beneficial for orthogenic differentiation, but less beneficial for adaptogenic differentiation. But in our examination of stem cell differentiation, both orthogenic and adaptogenic differentiations will be enhanced with increase of RGD nanoarray. But I'm still a bit less satisfactory with this conclusion, because if we change RGD nanoarray, both spreading area and differentiation have been changed. So how can you rule out the effect of cell spreading? By this way, we need to prepare a micro-nano pattern. In a micro-island, we strictly control the cell spreading area, and just on the very small cell adhesive microisland, we generate the nano array. Now, it is not very easy to draw it on the paper, but it's extremely easy for my student and my group to achieve such idea. So the first PhD student has not achieved it until he graduated. And then I arranged the second one. And the second one have succeeded in this experiment before her, and anyway, at the late age of his PhD study. Now, here is a demonstration of our pattern. You can see the micro pattern. You can also see the micro island. We can magnify it to see the nano pattern. So it is really difficult to obtain such a pattern. And we also culture cell, because due to our careful design of the size of the nano dot and also the size of the cell adhesive microisland, we can achieve the single cell adhesion. We can control the cell spreading area, so we can examine the differentiation effect along with both the microdomain size and also the nano spacing. Anyway, our conclusion is more deterministic and very interesting. While large spreading favors orthogenesis, and this favors adipogenesis, large RGD nanospacing is beneficial for both. So the RGD nanospacing, the why nanospacing is important. We hypothesize that the biconjugation of RGD and integrin is a necessary condition to trigger the specific cell adhesion, but it is not sufficient. The sufficient condition should consider the supramolecular structure of cytoskeleton. If the RGD nanospacing is larger than the critical one, for instance, 70 nanometer, the lateral cross-linking by alpha-actinic could not work. So the cytoskeleton cannot form a network. By this way, in biology, they are essentially different. So that is the underlying reason, the RGD nanospacing. Now here we can give the answer to be or not to be. For matrix stiffness or surface chemistry, our answer is both. And also based on our careful examination of cell adhesion, cell differentiation, on nano patterns and micro patterns and micro nano patterns. Now we have reported a lot of pure fundamental research. The last part, I will give a story from the pure fundamental research to the real clinical translation. In this part, the new input of our group is to reveal the relationship of cell migration and cell adhesion, again, based on our unique surface patterning technique. And also we designed an appropriate surface modification to enhance cell migration of biomaterials and developed a new occluder to improve interventional treatment of heart disease. Here is the schematic presentation of cell migration. The cell migration might not exhibit non-monotonic effect of RGD nanospacing. So I have just reported that for the cell adhesion, it changed with RGD nanospacing monotonically. But for cell adhesion, we found that it is non-monotonic. So here is some image about a human umbilical vein endothelial cell. Here is a schematic presentation of a polarized cell. So the cell, so I think that in the audience, many people are not really in the background of biology. You may recognize that the cell is just like a sphere. Actually, it is not. Okay, and it can spread on the surface, have the leading edge and trailing edge. We call the cell adhesion in the leading edge is the leading adhesion. It is relatively nascent. And also in the trailing edge, it is a focal adhesion. Of course, the focal adhesion was translated from the nascent adhesion. So we did a series of cell experiments on a series of RGD nanoarray. We did find that the monotonic change of cell adhesion with RGD nanospacing, and also we found a peak. The peak values are dependent upon cell type. However, all these peak values are larger than the critical RGD nanospacing, I mean 70 nanometer. Here is the summary. Even only in the medium RGD nanospacing, the focal adhesion is not very strong because it is over 70 nanometer, but the leading adhesion is strong. By this way, the cell migration is fastest. Now, here is the schematic presentation. We can imagine that in the case of moderate adhesion, it is not very difficult to form a new focal adhesion. It is also very difficult to disrupt another focal adhesion. So then the cell can migrate it fast. Okay. Now we have some new idea or we have some new insight about the cell material interaction. The surface modification of a regenerative biomaterial does not necessarily increase cell adhesion. And sometimes a bit decrease of cell adhesion might be beneficial for enhancement of cell. So for the adhesion could be beneficial for enhancement of cell migration. It is particularly meaningful for cardiovascular implants because in most of the cases for cardiovascular implants, rapid endothelialization is much required. Now, our clinical translation is about interventional treatment of heart to deal with heart disease using a occluder. Here is some the cartoon to indicate the function of the interventional treatment and also using the occluder. The demonstration is for the ASD, but both ASD and LAA have been investigated. But due to the time limitation, I just gave a story about LAA. What is LAA? Everyone has LAA. It's the left atrial appendage. Now here is left atrial appendage. It has no positive functions. However, if an adult has some atrial fibrillation, and then he probably is in a risk because the dominant source of thromboembolism in heart comes from the left atrial appendage. So if some blood clots dropped off and moved to the head, and then the stroke might happen. So one of the very efficient way is to occlude the LAA. And however, it has a huge market, but technically it's very challenging. So the real commercialization cannot meet the demand of the potential demand, because the technique is very difficult, and also it is much required to achieve the rapid industrialization. So it is very meaningful to have a surface to achieve the enhanced for the rapid cell migration. Here is the basic idea of our invention, and also it's for the internationally first nano-coated LAA occluder invented and made in China. We made the two-dimensional modification to enhance cell migration and the three-dimensional structural design for percutaneous intervention. Now, we initiated from a super elastic metal. It has been much used in the clinic. And we use some of the biceramics to modify the metal to avoid the nickel ion release. And to our surprise, we found for the first time that the human umbilical vein endothelial cell can migrate much faster on the nano-coated surface. We then, in cooperation with some companies, to fabricate the left atrial appendage occluder, and also we examined its efficacy in the animal, and then we did the clinical trial and applied in human body. So if one just simply to coat the titanium nitrogen on the metal, and then it is not stable. So we invented an alternative layer. By this way, the surface modification could be quite stable, but the outermost layer is always the titanium nitrogen layer. And we have not found a significant difference of cell adhesion and proliferation of human umbilical vein endothelial cells on surface with and without nano-coating. But we did find a significant difference of cell migration. So the much faster cell migration is very meaningful for cardiovascular implants. We also quantify the such behavior to examine the leaf cell migration, to quantify the collective migration and the random migration of single cell. It is very interesting that the random migration obeys the Brownian motion equation established by Robert Einstein in one of his famous papers in 1905. Now, it's really the mean squared distance exhibits a linear function of time. So by this way, we can obtain the diffusion coefficient. The diffusion coefficient on the modified surface is about double on the surface without coating. We also examined some bioinformatics analysis. We examined more than 20,000 genes and found about 2% of genes have been upregulated or downregulated. And we also use the qPCR and other techniques to detect the MIA expression and also the protein expression. So finally, we can realize that after the surface modification, a bit less cell adhesion is beneficial for the cell migration. And we also fabricated the 3D structure and by this way, the device can be put into a large animal by interventional treatment. These data are very valuable about the left atrial appendage osteo. So you can see the before occlusion is very significant. As well as after the implantation, it becomes much less, and the the blood flow almost disappeared after 3 months. We also took off the occluder to examine the surface, and we did found the rapid endothelialization as soon as 1 month. And also we quantify the estimated speed of cell migration in vivo, and also consistent with our in vitro experiment. We did the clinical trial. You can see the process. Here is an image for the digital subtraction angiography. And then I show a clinical case to demonstrate the implanting process. Now, the doctor used some angiography and sealing disc deployment. If we found no residue flow, the sheath could be retracted. Now we finish the operation. Now it is really, our cooperation doctor is really very, very skillful. And also the device is convenient to use. Here is a basic procedure for the angiography to show LAA, umbrella deployment, cover deployment, residue flow examination, and the successful occlusion of LAA. We also employed the transthoracic echocardiography to did the follow-up assessment. And this follow-up assessment indicated the great success of our new medical device. So after many experimental evidence, and also based on our fundamental research, the company put forward the application from the different official bureau. And the occluder has been approved in European and China, and have been used by many patients. So before we, just during we drafted our publication, it has been used by about 70,000 patients. And now it has over 7,000. Now it has over 10,000. Here is the countries and the regions which have, the patients have used our new and advanced medical device. The number has been increased very rapidly. So anyway, by this way, we have combined the fundamental research and the clinical translation. We modify the surface to enhance cell migration, and also invent a new occluder to improve interventional treatment of heart disease. Now I give a summary about the novelty of our work. We established some technical platform. This technical platform can be used to reveal some basic science. Otherwise it is very hard to be revealed. Guided by the science, we developed some facile surface modification technique, and also invented a new occluder with nano coating, which has been clinically translated. Now I will give a brief introduction of the main research branches in our group. One is the cell material interactions based upon patterned surface. The other is tissue regeneration scaffolds, and also polymeric controlled release carriers. For the first one, our material technique is complicated, but the science would like to be very clear. And for the second one, we would like to have our technique as facile and reliable as possible, because it is more convenient for the clinical translation. And so far, our group have invented a lot of techniques. For instance, the biodegradable polymers, injectable hydrogels, polymer biceramic composite, metal polymer composite surface modification, and also have a lot of applications or potential applications in cardiovascular, in orthopedic, drug delivery, and also some the biosealing, and also from some other applications, even in cosmetics. Here is a very current a very current image of our group. So we are open to cooperate with many scientists and the students from the different disciplines. So that's all for my talk. Thank you very much.
Thank you very much, Professor Ding, for fantastic talk that really, give us a beautiful, story from fundamental understanding to the real application. I really enjoy it. So I guess now we're going to move to, questions from the audience as well as a very short panel discussion. So first, I've got a couple of questions from the audience. The first one is about the size of the nanoparticle that you use for the your nano array patterning. So basically, the question is about the dimension of the size and what's that influence on the results, and its effects on the results.
Yeah, it is a very good question. And the size of the nanodot can influence the cell behavior, of course. So we control the size a bit less than 10 nanometer. Why less than 10 nanometer? Because the size of integrate is about 10 nanometer. If we prepare the nano array with a nanodot a bit less than 10 nanometer, although 1 or 2 or 3 RGD could be linked to the nanodot, only one RGD ligand can be bioconjugated with integrate because the first bioconjugation will afford a steric hindrance to the further bioconjugation. That is the main idea of our work. So in brief, our size is about the 10 nanometer or a bit less than. Here is the characterization of our AFM image. Now, that's.
Yes, thank you. And I've got the second question from Alan from the University of Pittsburgh. Are the stiffness-dependent cell behaviors different for different cell types?
So the question is whether or not matrix stiffness exhibits cell type dependence. Is it true?
Yes.
Yeah. According to our research and also some publications in other countries, we found most of cells, if they can anchor on the biomaterial, they exhibited matrix stiffness effect. Of course, the most sensitive, they also have some most sensitive range of matrix stiffness, but we really found that most of cells can show the effect and the sensitivity to the matrix stiffness. So I called it a milestone in the history of cell biology and regenerative medicine and also biomaterial. It is really a great discovery. Yeah.
Thank you. Now I would like to also welcome our panel member panels to the stage, the Professor Paul Weiss and also Alice, to actually ask questions as well. Paul, do you have any questions?
Yes, I just was hoping, and first of all, sending our best for you and everyone in Shanghai now. I was wondering if you might take us through how you choose problems like this. We also engage very strongly with medicine here at UCLA. We're just across the courtyard, and maybe you can tell all the people out in our audience how you're picking a specific problem and approaching it.
Yeah, it is a big question. I think that Professor Weiss is more qualified to answer this question, but I would like to try to give some answer. And I think it also depends on the type of research. In my group, we are more interested in some interdisciplinary important scientific question between the biomaterials and the cell biology, or between material science and biomedicine. So sometimes we are more interested in the so-called the important question. It should be resolved before to improve the advance by the drug delivery or biomedical device. But also sometimes, to be honest, I just am very curious with some questions. I also think it is important. I don't know why, but anyway, I think it's very fundamental. I don't know whether or not it is useful, but I'm just curious. So in my group, we usually are more interested in two kind of questions. One is really important for the R&D of the more advanced drug delivery and medical device. The other is simply just because we are very interested, because it is very fundamental. I don't know whether or not you are satisfied with my answer.
Great.
Okay, I have to add one more thing. So, Paul, you may know that Fudan University have a very good hospital. Yeah, they have a very good medical school. I think Professor Dean has good collaborations. Yeah, with their hospital and the doctors. So that's why all this work can be so smooth. I have one question for Professor Dean. Yeah, I see in your last part you have a very beautiful structure. Was implanted, into the body. So, I mean, you say that for coding and uncoding will be much more different. So I'm thinking, did you code something as hydrophobic or hydrophilic or this thing, or this kind of functions, or just code some kind of nanoparticles? Yeah. So what kind of function?
Yeah. It is a very important effect of the hydrophobicity to the cell behaviors, because if a surface is hydrophobic or hydrophilic, it will influence the non-specific protein adsorption and also the non-specific cell adhesion. It is another story and also very important. My group has also some work, but due to the time limitation, I have not concerned. I gave some the very strict selection for my talk tonight. Yeah.
Okay, because I'm thinking you should treat it hydrophobic or hydrophilic, folic, because if once the implant device was very high adhesion, with the organs, that must be one function. If we want not, highly adhesion to the organ, they have to another. So that's why I'm curious on this. Yeah.
Yeah, but in most of surface I talk tonight, they are eventually hydrophilic.
Okay.
Yeah.
I see. Okay, that's very nice. My question was finished.
Yeah, if I may, I might just ask the last questions. As a material scientist, I'm really
you're welcome.
very interested in your large your nanolithography technique.
Yeah.
I just wonder how big you can really do this lithography. Like you're handling with quite small micro patterning and all this, but overall, how big you can really apply this this lithography technique to the substrate?
Yeah, it is an important question. Some patterning work, they are very elegant, but it's too small to culture cell. So in our work, we will prepare micro pattern, nano pattern, and a micro nano pattern. It should be significantly larger than the size of cell. Actually, we prepare our pattern on the standard glass slide for cell culture. So it is sufficiently large for cell studies. Yeah.
Okay, thank you. With that, we might have to wind up this talk. Thank you very much again, Professor Dean, for a really, really interesting talk. And also thanks our panel today for joining the discussion. Now I would like to pass the microphone to the speaker, to Alice for the next talk. Highly anticipated talk.
Okay, yeah. So live, we found the one thing. We deliver certification to Professor Dean. Yeah.
Oh yes, please.
Okay, Professor Dean, we will deliver this, lecture version certification to you later. Okay.
Yeah. Yes. Thank you.
Okay. Cool. Paul, please.
Very good. Well, welcome everyone. I'm Paul Weiss from UCLA, and I am delighted to host our next speaker. Chen is the Carl Richard Soderberg Professor of Power Engineering at MIT. He was previously here at UCLA and left quite a legacy here as well. In fact, right after this, I'll be working with one of his former trainees here. He served as the department head of mechanical engineering at MIT from 2013 to 2018. He received an NSF Young Investigator Award, an R&D 100 Award, a number of awards from ASME, the World Technology Award in Energy, the Enrigan Medal from the Society of Engineering Science, and the Capers and Marion McDonald Award for Excellence in Mentoring and Advising at MIT. He's a fellow of the American Association of the Advancement of Science, the APS, ASME, and the Guggenheim Foundation. He's been elected to Academia Sinica, the American Academy of Arts and Sciences, and the U.S. National Academy of Engineering. We're delighted to welcome him back to science here. And the title of his talk today is Photomolecular Effect. Gang, the floor is yours.
Good evening, good morning, and good day, wherever you are. Thank you, Paul. It's so great to see you. And thank you, Alice, for your kind invitation. Because this, I'll share, can you see my screen?
Yes,
Yes, yeah, not in presentation mode yet.
Okay, yeah. I'm going to presentation mode.
Perfect.
Alice told me that this event is part of the 70th birthday celebration of Huazhong University of Science and Technology. So let me start with happy 70th birthday. I entered into Huazhong University of Science and Technology in 1980, so it's been 42 years out of this 70, and really, I want to say thank you to Hust because the study and the work there for 9 years really laid the foundation for my career. And today, I'm going to talk something that is really new. And we do not know, we do not fully understand it. There's no impact yet. And I'm very impressed with Professor Dean's talk. But I want to say the talk I gave is very fundamental in nature. And I think it probably will have big impact, but we don't know. And in fact, we do not actually understand it. And we also have trouble to convince people that what we observed is true. So I'm going to talk it and post it also as a challenge to the community to verify it, to say we're wrong, and to make progress, because some of the observations to us are really exciting. So we call this observation photomolecular effect. And I put a small title here, evaporating water using visible light beyond thermal limit. And I want to also introduce Dr. Jiandong too, because most of the experiment is done by Dr. Tu. So I'll mention more along the way. It just also happened, Jiandong also got his undergrad from us. So because we have trouble to get convince people, and so we put the talk materials online. This is on archive. You can read the papers and raise the objection or have your own experiments. So we welcome the audience who are interested to actually look more into what we observe. So what I'm going to talk is a very common phenomenon, evaporation. And we know evaporation is an everyday life experience. And the evaporation water needs heat. So we call thermal evaporation, right? We do cooking, we see evaporation every day. And we see the clouds, we see the fog. And eventually the sky, the clouds gone, the say clouds are just water droplets and a similar fog, and they are evaporated. And of course, we think all evaporation need heat. So we call thermal evaporation. For water, how much energy we need, it's easy, right? We know the latent heat of water, that's about 2.4 or 2,400 kilojoule per kilogram. And if we want, well, there's some temperature change, we can also include the specific heat, but latent heat is the major part of the energy to evaporate water. So this is everybody knows daily experience. And of course, when we think about the fog, the clouds, it's interact with sun, right? And the problem is solar radiation in the visible spectrum, water does not absorb the energy. And in fact, on the left, you can see the top of the different color of the solar spectrum, and green is the strongest, but green light on the left bottom, you can see can actually propagate 40 meters in water. And that's why we say the bottom of the, say, clear water, lake, and river. So if we want to use solar energy to evaporate water, the typical way to do it is to convert it into, I want to use my spotlight, and to convert user absorber. So these are examples of using solar radiation to evaporate water. And of course, there are many different ways to do it, as long as we convert the sun energy into heat. And some recent work, including Naomi Hallas using metallic and nanoparticle into water as absorber. And about 8 years ago, we thought about another way. Let's float some material, absorbing material, in this case, really a carbon form, and floating on water, and it's porous, so you can suck up water through surface tension, and the solar energy can focus on the surface. And in that case, only the surface gets hot, and the rest of water still cold. So you can get a quite efficient solar to evaporating water. And it turns out that there is a fundamental limit on that. And this fundamental limit is we know how much energy has in the sunlight, and in standard term is about 1,000 watts per meter square. And you convert that energy into 1 hour, how much energy it has, and they say how much water it can evaporate. And the value is about 1.4 or 1.5 kilogram per meter square per hour. So this, you can think as a fundamental limit, right? That's how much maximum if you convert all the solar energy from the sun into heat, and how much water you can evaporate. So after this work, and in fact, we're not the only one, and there are others involved in this. And but after the work, there are more people jumped into this topic. And surprisingly, in 2018, a group from Professor Guihua Yu in UT Austin reported using hydrogel, which is a polymer, and added with a black absorber, making a porous material, and the evaporation rate actually exceeds the theoretical limit. right? So here is a pure, the green line is a pure water, and the dots, they have the red dots here. You can see it can go as high as 3, which is really over 2 times of the thermal limit. And Professor Yu and their collaborator proposed this is probably because water in hydrogel are different from the bulk water. So they say they're bound water, intermediate water, and the free water. And they also mention possibility of water has clusters. So their picture is still okay, has a reduced latent heat. So with that, they calculate efficiency still within 100, less than 100%. And honestly, at the beginning, I did not believe that. And I talked to people, and most people do not believe the results. But in 2019, I got Dr. Jiandong too from Shanghai Jiandong University came to my lab, and also Miss Hongxia Chen, who was a graduate student at the Huazhong University of Science, and she is a chemist. She came to my lab, and at the time, a graduate student Jiawei Zhou, and collaborating with Professor Xuanhuo Zhao's student Shaoting Lin. And at that time, we were working into hydrogel, thermal transport in hydrogel. But since Jiandong was interested in the solar evaporation, and Hongxia was a chemist, and I said, okay, why don't we also learn to make the same material as Professor Guihua Yu and try to repeat their experiment? So we started, even though we knew how to make hydrogel, but it didn't work. And in fact, on the left-hand side, the middle here, were actually the hydrogel I made. I got excited last year. I got into lab, I made some sample and didn't work. But so I took sent the 3 of my group members, Jiawei, Jiandong, and Hongxia, to Professor Yu's group, and they kindly hosted them for a week. And I brought a sample back. And turns out that we still, even after a week, we still couldn't make the sample. And it took another few months for us to really master the sample making. But the sample we took back actually worked. It did show evaporation under sun can exceed the thermal limit. So that convinced us. So we did more of a sample synthesize, optimizing, and eventually we can get to the level they reported. But of course, those are the results already discovered by Professor Guihua Yu. And the question we ask is, can we further understand what's really going on? So rather than using solar, we started to use light emitting diode, LEDs, because that has a different wavelength. And to our surprise, on the left, you can see that the evaporation rate actually depends on wavelengths. And it peaks at the 520 LED wavelengths, that's a green light, where the sun, say the water does not absorb, the least absorbing of water. And so that's some hint, this might be some photon effect. But we didn't know what was the photon effect. And then when we look at the temperature in the vapor phase above water, it's also very strange. You can say the blue is when the light turns off, and the yellow is when the light turned on. But when the light turned on, the temperature is lower. And then there's a region where the temperature above, say, is actually flat. So very characteristically, very different from the thermal evaporation. So what are this photon effect? Could that be hot electron? Could be the PV molecule? And for us, it's all negative because Professor Yu's group had demonstrated they could use different absorbing material and they could all get to the similar effect. It can be hot electron with you have different absorber like titanium dioxide, polypyrrole polymers, and even graphite. And what about the molecule themselves? This is a polyvinyl alcohol, and we know the material does not absorb in the granite. So we were at lost. We didn't know what's happening. And at the same time, Professor Yu had a lot of very interesting results, and I mentioned they have this 3 water picture. And one experiment that really intrigued us. And this experiment, they put a pure polyvinyl alcohol hydrogel on a carbon paper. And in this case, to our opinion, right, pure PVA do not absorb sunlight. So sunlight get to the back carbon and they heat up. So that's the thermal effect. So probably they're right. And we also did some differential scanning calorimetry, and sometimes you could see reduced latent heat. And Professor Yu, they reported, but the latent heat reduction can never really come to the level of experiment because it's only less than 30%. And but on the other hand, we say, okay, maybe it is a thermal effect. And this was actually around the end of 2019. And 2020, we spent the whole year trying to show whether thermal effect can explain. So in this case, if it's a thermal, you can heat up a different way. You can use electrical heating. Of course, you try to get it as close as to surface because solar heating is near to surface. So we try to make a uniform heater, but also porous. Turns out that it's not easy. And we try to push closer to the surface. And you can see different distance from surface. On the other hand, you can see the evaporation rate never gets to above the thermal limit, 1.4, 1.5. We don't get that, right? So of course, COVID happened, a lot of things happened. And, but say I had some time and I did more study. And I found actually many people have reported solar evaporation over thermal limits. This is after Professor Yu's group. People use different absorbers, right? Polypyrrole, titanium dioxide, different polymers, and even non-polymer materials, carbonized fruits, purely carbon. And some of this result is 3 or 4 times or 5 times the thermal limit. And that's puzzling. And our push to interpret the heating never worked. So this forced me to come back last July 2021. And I say, well, maybe we need to go back to the photon effect. And the question is, what could be the photon effect? What are common among all those materials? And it just happened to me that the only thing common is large surface area in this porous material. So it could be a surface effect, could be photon absorbed at the surface. And I knew there was one example. Professor Dean mentioned Albert Einstein. And this was also Albert Einstein. And he explained that the photoelectric effect that was experimentally discovered by Hertz. And of course, anyone learn physics learned the photoelectric effect. And when the photon lock at a metal surface, if the energy is higher than the work function, then it excites the electron above the metal surface and create a current. And this is Einstein's idea, which at the time really was revolutionary on one hand, but also qualitative on the other hand, because there was no model. The only model was the energy level, right? But it was a revolution because it brought the idea of photon is light electromagnetic wave is a quanta, energy quanta. Anyway, that was the inspiration. We say, well, this might happen in water. But there are two problems. One is that water doesn't absorb. Metal has a lot of electrons, can absorb, that we understand, but water does not absorb. And second, energy does not match, right? Photon energy at green light is 2.5 electron volts. While the bonding energy between water molecule, the hydrogen bond, is 10 times smaller. So how could this happen? It turns out I was studying water and learned that the water, even though it's a daily, we drink water, but scientists really do not agree with water. It's one of the most complicated fluid to study, liquid to study. And people do agree there are a lot of hydrogen bond and that form clusters or networks of hydrogen bond. So then it come to me that if their cluster really come out, there are a lot of surrounding bonds energy, they add up. Yeah, they could match the energy conservation. So with that, let's say the question is, does PVA, polyvinyl alcohol, absorb if it has a lot of surface? So with that, I redesigned the experiment with Jiandong, and he was very brave. He never done those kind of experiment before. And so we tested water absorption in pure hydrogel. And you can see on the left, right, as gelated polyvinyl alcohol and water, the absorptance we measure. So we measure reflectance, transmittance using integral sphere, so we can measure scatter light also. And after that, we do subtraction to get absorptance. And you can see in the visible spectrum, water, pure as gelated polyvinyl alcohol, none of them absorb. But after you freeze dry, it becomes absorbing. And in fact, if you take a dry hydrogel, that's middle curve, middle figure. If you take a dry hydrogel, you put a little water, you don't flood the entire hydrogel with water, it becomes highly absorbing, right? And the absorbance is somewhere between 15 to 20%. So this was the first, sign that we were on the right track, because long-absorbing material become absorbing, probably because this surface effect. And then we did more evaporation experiment, and you can see, even without any absorber, pure hydrogel, this is the figure A, you under light, the evaporation rate suddenly increase compared to, so you need to have the water recess into hydrogel to have a surface area. On the blue region in figure A is when water cover the top surface, you do not see anything special, but once water recess into the surface and they got more area exposed, you have suddenly increased rate. And this also explained Professor Yu's previous experiment using pure hydrogel, put a carbon paper, and we can see if we put a solar through the backside, that's a purely thermal, we do not have that effect. That's a figure B in the middle. And then, but if you go from top, it has that effect. And then figure C shows if we do the evaporation rate, right? For pure hydrogel, after we normalize to absorptance, it actually is the highest evaporation rate. and way beyond the thermal limit. So, and also we did a LED, and interestingly, even pure hydrogel without any absorber, the peak happens at the green light, 520. And lower intensity on the right actually give us even highest evaporation rate. That's the blue curve you can see. So those are what's happening on the evaporation rate. And I, again, pushed Jiandong. I said, I want to say a smoking gun. Can we say, if this is a really exciting water cluster, can we say in the vapor phase? So we went to vapor phase again, because vapor phase, we saw the flat temperature region in 2 years before this, right? And in the pure PVA, we saw it again. You can say there is a flat temperature region. That's the bottom is a pure water, and never has those. And the explanation now we have is that when photon excite the water cluster into vapor, the cluster break up. They actually absorb heat in the vapor phase. So they first absorb heat. That's why there is a cooling effect. And then when the vapor gets saturated, then you got a flat temperature region. That's why we have flat temperature region. And this was still not enough. I say, can we see the signature of cluster, right? And this actually say, you can see the video. So we measure the vapor transmission spectrum above the water surface, and we have UV waves. So we actually tried the infrared Ftir before. That's 2 years before this. We didn't say it because we don't know what to look at. But this time we saw it. We use UV waves. We see you can see 2,700, right? And that's the vapor water spectrum. And you can see as you go higher and higher on the surface, a blue shift. And that's because the water cluster becomes smaller and smaller. So this gives us a lot of insight, and we believe that this is a photon effect and the surface effect. And here is a more physical picture of what's happening. We call this photomolecular effect. And I want to say this is the one that we could be completely wrong, okay? And but this is what guided our experiment. And it's a physical picture, but we don't have any model. And but see, here's what we think was happening. You have a light come in, and you have to have a light at the angle. And of course, in porous material, there are a lot of angles, right? And so in this case, electromagnetic wave is a transverse wave. And when you have an angle, then there's the electric field perpendicular to the interface. And then when you have an electric field perpendicular in the interface, you look at the middle, the Maxwell equation say the displacement field is continuous. So dielectric constant epsilon1 times field equals epsilon2 times field. But epsilon1, epsilon2 at the visible light, they differ by a factor of 2. So over a distance of a few angstrom across the interface, there is a factor of 2 of electric field change. And now if I have a polar water molecule, which is 1 angstrom, right? Or say within 1 angstrom, or between 2 water molecules, which is 2 angstrom, and the cluster larger, the positive and negative ions of water charge, say molecules, say atoms, they experience a different magnitude of electric field. So in a uniform electric field, a dipole doesn't move because the force cancel, positive and negative charge force cancel. But in a highly non-uniform field, the force is imbalanced, and that can drag the water molecule coming out. But what about the energy matching? Is it a quantum process, right? So this is where the cluster picture, we think it's a quantum process, and I'll show you more, where a photon come in and really can excite many molecules. This N is a number of bonds of those cluster with surrounding water. And that way it can excite the cluster to the vapor phase. So we are using a real analogy to the photoelectric effect, despite that water molecule does not absorb. But this is, like I said, this picture is what's in your mind. And it could be very well revised by other people, and there may be other mechanisms. In fact, I'm talking to a lot of people because these are very actually hard to believe. But for us, the question is, can we observe better? Can we see more of those effects? Because the porous material is really, there are a lot of surface, very complicated. So in October last year, I told Jiandong, I said, let's try pure water surface. Maybe we could see something. But I didn't expect to see really big effect. And this surprised me, the less. So we did a pure water experiment under light, LED. So it's very simple, right? And you have balance in the middle, and you have water in a glass container, and we use LED light emitting, and we also use laser diodes. And this experiment, you need only a few $1,000s to set up. And the evaporation, we took a green light first, 520, and at the angle of incidence 30 degrees. And this is the weight, measuring the weight loss. From A to B is lateral evaporation. There's no light. At point B, we turn on the light. And we saw B to C. This is amazing to us. We saw the weight rapidly drop, but the rate slowly decrease. Come to C and D, they are almost parallel to A and B. And then what's amazing is that you turn off the light, the weight recover. So it's like a light lift up a bucket of water and put it back when you turn off the light. We call this a photo levitation. And really interesting to us. And the peak, it has an angle dependence. If it's a lower incidence, you don't see that effect. But it peaks at 30 degrees to 40 degrees. In fact, I told Jiandong, I had a very simple model. I said that should look at the 54 degrees, but the experiment saw it's 30 to 40 degrees. So we do not understand this yet. But it happens to visible light. And once you go to green, the red light 650, and you can see the effect is very small. And when you look at the wavelength dependence, and this is even more amazing, right? Like you subtract out the lateral evaporation, and you see it doesn't happen beyond red light. Just let me just say we only have this many wavelengths, so we don't have a lot of wavelengths. And in fact, the LED light has a spread, so we don't know exactly where it's cut off. Okay, but this is very similar to photoelectric effect, and it's a sign we think this is a quantum process, like I explained before, photon lockout water molecular cluster. And this is another check where we use polarized light because we need the electric field perpendicular to surface. So if you have a transverse electric field incident, this is using a laser, it doesn't happen. So TE, you can see when the laser is on, there's no reduction in evaporation. But if you have a transverse magnetic incident, there is electric field perpendicular interface, and there is evaporation. And we also saw the intensity dependence once you go higher intensity above 1 sun. So it's actually really interesting because we think this is a water cluster reformation needs time. And the temperature history, so why it actually, at the beginning, when light turn on at B, you have fast evaporation. And then we look at the temperature history on the surface, you can see this blue light, a blue curve. First lateral evaporation, temperature drop about beyond the, say below ambient. When light turns on, you can see between BC, the rate decrease, but the temperature increase. So what's happening? And this is the same picture. When light comes up, it will excite the cluster. But when you, as a cluster accumulates near surface, then the next cluster coming up will be reflect back. They will recondense. So they will actually generate heat. That's our picture. And eventually, because the surface is cold, the only way for molecule to get away is by diffusion. So it really depends on the ambient. So that determines why eventually C and D is parallel to A and B. And now when you turn off the light, this cluster can recondense back. That's why D and E, the weight recover. And in fact, that recondensation, you actually see a small temperature increase. You can see between D and E, there is a small temperature increase. So we think we can explain this. And in fact, using this temperature rise, we have trouble to measure the absorptance directly. We're still trying. But using the temperature rise, we could infer what's the absorptance. So we measure the temperature rise. The left-hand side, you can see at the blue, it peaks at 30 degrees. And the red is become a thermal evaporation. So we can see how much absorptance. This is the right-hand side is what they infer. It's actually a huge number. This is really surprising. We're still trying to check, okay? But see, using this, we can calculate one photon can excite 50 to 60 molecules. This is almost 9 times more efficient than thermal evaporation. And we still want to go to see our silver bullets and the vapor spectrum. And so this is a measuring the transmission of the vapor. And in this case, we actually heat up the water because when we do not heat up, we cannot measure it. The cluster is too close to surface. But we heat up the water, we measure the red is when light off, the blue is light on. You can see when light turns on, the water absorption happens very close to the water vapor. This is a water vapor absorption and close to, but it's continuous. That means it's more than one water molecule, not a discrete water molecule. Those are the clusters. So we think there are more spectral information. And all this is called consistent. And the last experiment I ask Jiandong to do is, okay, this is interesting. And because let's try to make it relevant, right? Let's look at cloud, because currently cloud evaporation, there's one more picture than before, temperature I mentioned. So temperature also has a flat region. Even above water, there's a flat region, right? You can see the flat region. You can also see when light turns on, the temperature rapidly drops near the interface. That's because the molecular clusters are breaking up. So in this case, light actually creates a cooling, not a heating effect. And this is the cloud I was mentioning. And we say because in all the current cloud model, right, it's a thermal evaporation, but water does not absorb visible light where the sun is strongest. So the question asks, does water heat up the green light, heat up water fog, right? Clouds using green light. And you can say this is a fog chamber. It's filled with water droplet generated with ultrasonic vibration. And then we shine, compared to, there's no fog, all right, on the bottom. Then we shine the LED of different wavelengths, same intensity, and you can see exactly at the green light, the evaporation surface temperature is highest. So actually, visible sunlight does heat up fog, does accelerate the cloud evaporation. So at least there's implication for weather forecasting and the global climate. So those are the really very recent, as you said, we haven't published any paper, we just put it online and we hope to get more interest, but there are a lot of open questions, right? Is this effect widely happening in clouds, fog, ocean, soil surface, plants even, right? There no reason it does not. We already show it happened to fog. So there are really significant implications to us for climate models. Does this happen in other liquid? I think likely. And in fact, we have preliminary data to show yes. And so there are a lot of liquids we can test, and we really do not know all the criteria. Where is the peak? And of course, is our current physical picture correct, right? It's hand waving. There's no model, mathematical model. It's just a physical picture. And I talked to a lot of people. I would say most people don't believe yet. So it's open to the whole scientific community to criticize, to find a new explanation. We welcome all those. And how do we quantitatively characterize the effect, right? And absorptance, there's some difficulty in measurement. We're still trying to solve this. And how we quantitatively model those effects. And of course, how we use this, right? And we are looking to some applications. But this is a really wacky thought, but it came immediate to me. So I have to talk about it. Because the sunlight is like green, peaks are green, and the leaves are green. So why leaves are green? You talk to biology, they say, oh, this is because of chlorophyll. But chlorophyll, why chlorophyll evolved? So this is a more evolutionary question. Why chlorophyll evolved to avoid the green light? Is it because they are losing too much water due to the photomolecular effect? Because this evaporation rate is the highest at 520, right? So we don't know. And I talked to some biologists, some say this is interesting hypothesis, and others say, no, it won't happen. So let me summarize. Really, we think of this direct photon evaporation, the effect we measure is true. There are a lot of signs we call the photomolecular effects, right? In pure water, we say wavelength dependent, angle dependent, polarization dependent, and we saw in the signature in vapor spectra, we saw in temperature distribution. And similarly, in hydrogel, we saw among all this, we also saw super thermal evaporation. And we think we can, just like a photoelectric, there are internal, there are external effects. And then we also, they observed, say, photomolecular levitation phenomena. So with that, let me end up my talk here. There are really many people to thank. I thank some people for the photos, but mentioned the Professor Guihua Yu's group. They're very generous. And actually, say Professor Xuanhuo Zhao helped manage my group in different time. And many other people we talk and discuss, and really also thank the entire scientific community for your support. Thank you very much.
Great, Gang. Yeah, that's so proud of you. Yeah, you come back, you give such a very nice story. Yeah, many, thinkings here. So yeah, we go to the panel discussion. And this time, many people waiting online to ask questions. So first, let me introduce our best friends to get on the stage. Yeah, we have two panelists. Let's welcome Chen was from Huazhong University of Science and Technology. Is your alma mater? Yeah, it's the professors there. And we welcome Jiandong. Yeah, too. You mentioned his name. He's also the co-authors for this talk. Yeah, Jiandong. Yeah, welcome. We also have Lan, Fu, and Paul. Yeah, the warm welcome from iCANX. Okay, Paul. Yeah, I think long time no see, right? Yeah, so please.
Well, thank you so much for the talk and laying out the problem so nicely. I wonder if you've looked at ion concentration and pH. I'm reminded of the late Will Kessman's work trying to explore if there really is such a thing as hydronium, and then seeing as a result solvation shells of water around what turned out to be, it looked like an H3O plus, as one sees for ions, and if there might be some organizational effect in those cases that you could that you might leverage or at least test.
Paul, that's a great question, and we thought about that. And in fact, we did some tests, and we're still testing the ion effect. And I think there we saw effects, and but we don't have very systematic data yet. On the other hand, the question is whether is really charged ion or ion pairs, right? So if it's an ion pairs, we think it's ion pairs coming out if there this effect, because otherwise we would see very strong charging effect, right? So let's suppose you just got either positive or negative ions coming out, then you got a huge potential difference between the vapor phase and the liquid phase. And we check that, we have not seen that. So we so if there are ion effects coming out, then it's still what I call this. Well, the picture I said that their positive negative ion, their force do not cancel out. This is a quadruple effect at the interface. There still might be the mechanism. We don't know yet. This is a great question.
Okay.
Thank you.
So yeah, Lan, I maybe should introduce Lan to Gam. Yeah, Lan is from Australia. He's our new partner on iCANX. Yeah, so Lan.
Yes, thank you. We've talked before, I think, Professor Chen. It's a fascinating talk. My question is about the photonic effect there. When you're using this different porous substrate like hydrogel and those porous substrate normally will interact with your light, right? So how that will really affect the whole sort of theory? Can you really design some experiment to really narrow down that?
Nan, thank you very much, and great to hear you join the iCAN and iCANX. And that's an excellent question. In porous material, light gets scattered many times, right? Light trapping, this effect explored widely. We worked on solar cell. Light trapping is something that's very important. And there's this Evaporation limit, which is how much you can increase the absorption depth for n squared. And if you take the Evaporation limit, you will never be able to explain the absorption, because the pure water and the pure polyvinyl alcohol, they do not absorb. And the 4n squared will not help you to able to explain those phenomena. So, but can we work on different material optimize? Absolutely. This we hope. In fact, this is what I believe. Now we have a surface phenomena, right? And it seems we can engineer a long-absorbing material into absorbing without the chemical effect changing of the structure, right? So of course, most of the time when we want the absorbing material, we need the electronic or photonic the energy levels match. But it looks like we can now have a third way, using the surface, creating a lot of surface, and the physical effect to create absorption. That is it's a hypothesis, right? Everything I said, the physical picture is a hypothesis, but if you believe in this hypothesis, you could really explore a lot.
Indeed, it's a bit hard to actually decouple the traditional idea of just absorption there, I guess, a lot of things, but the new sort of concept you introduce here, we have to use a different way to think. I guess that's what I learned from here.
Yeah, we are learning, and like I say, I in my slides I talked to a lot of very famous people, and they gave me a hard time, so they made me to think, and made me to just make all my declaration. We might be wrong, but this effects fascinated us, and also I think this is a really the scientific discussion, and just to say what we dream of what we could do with this.
Yeah, that's super. That's really a discovery journey. Yeah. So Chen, welcome. Yeah, from HUST. That's a keyword.
Yes. Yeah, Professor Chen, it was really nice to see you on the stage and give us such a wonderful talk after such a hard time. Just to follow up with Lan's question, because I'm a surface scientist, and we usually utilize the flat, like a very, very ideal surface to do all this kind of absorption experiments. And we also use, just as you mentioned, Ftir, etc., to see the exact absorption, etc. So the experiment you just show is really sort of inspired us. My question here is, because the water or PBAs, they're all polarized sort of chemicals. And have you ever tried to utilize or think of some non-polarized chemicals or this kind of things to check about that? Yeah, sort of decouple some of the effect there. Thank you.
Very nice to meet you, and say another hoster online. And that's it's a great question, and it's really good for me to talk to surface people work on surface science like you. And indeed, we actually measure the nonpolar liquid, and so far in the spectral range we could not see any effect. But whether we could say in other spectral range, we don't know, right? So, and also you mentioned the flat surface, and this is another thing that is special with water, and the water surface is never flat, right? And in fact, we were in discussion with, I have a really interesting new student supposed to come in, and from Tsinghua, and he said, oh, it's a surface wave. Yeah, there could be surface wave, and water surface has thermocapillary waves. So all those possibilities, we cannot rule out. We are not convinced, and we are still looking into them.
Thank you. Yeah, I think that's definitely quite interesting to see if, in the future, we can find some photomolecular effect for non-polarized molecules as well. Thank you.
Okay, before we came to the next round for the questions, now I have to ask a question for Jiandong. Yeah, so Jiandong, you done a lot of work in this, in this work. So here is one question for you. Why the blue light leads to a smaller, photomolecular effect? This was from one people from Shenzhen. You say why is the blue light, lead to smaller, photomolecular effect? Please.
Oh, okay. Yeah. So first, thanks to Alice invite me here. Yeah, I think that's a good question. So I think we are still thinking more, try to understand it. But here, I can share some primary thoughts about why the blue, yeah, the blue light, how to say in theory, when blue light, the photon have high energy, but the photomolecular evaporation rate is smaller. So our explanation is this. So for the evaporation, it's how to say what it's related about the cluster theory. So so because the light intensity is one sound, it's all the same at different wavelengths. So for the blue light, one sound, that means how to say fewer photon numbers. So this is the first thing. But another thing is it also related to the absorption. So for blue light, it's penetration depth. Here we call it penetration depth, but maybe it's not very rigorous. So for the penetration depth for blue light is much shorter. So maybe only very how to say, very thin layer of water involved this effect. So both these two sides. So we think it can roughly explain why the blue light only excites a smaller photomolecular wave. Yes.
Okay.
Probably I add
complete.
the third point. This is coming back to the Einstein's picture, energy matching. Let's suppose only certain cluster can be cleaved off, so that energy is fixed. Then the blue light has a higher energy photon, and that excess energy is actually wasted as a kinetic energy. So the cluster coming out as a higher velocity, kinetic velocity. So that's this will be the same effect in the photovoltaic cell, where you actually waste that blue light excess energy above the band gap, and in this case is to the vacuum level, the energy. So we have a less photon, we have a less, say we might waste some of the excess energy as kinetic energy.
Okay, that's very nice. Okay, yeah, we came to the next round of the questions. Let's start from me. Okay, yeah. So I think we talk about some fun life. Yeah, when are young, we stay. Yeah, several of us stay. In HUSD, the beautiful campus. So what kind of good memories, the best memories you have there? So Gang, can you share with us?
Well, there are so many memories, Alice, and I stayed there 9 years, and right, and my living memory is my wife. I married her, say, right, I met her there. But just to give you a fun, fun memory. I remember there was this really heavy rain, and the west. I lived in West number 6 dormitory, and outside was the sports ground, and probably the water is above the knee, and we got so excited that we went out and played soccer in the in that say above knee water field. And although I never really was good at playing soccer, but I just remember that was fun. When you're young, you could have a lot of fun things.
Yes, it is a very nice memory. Jiandong, did you have any thing to share with us? So something special?
Yeah, since yeah, as the host for more than 7 years. So I think that's very I think it's the very good time. So yeah, so 7年园, yeah, it gave me a lot of happy time.
The garden for
Yes.
the youth, right?
Yeah, it's very beautiful. I think most in this time, yeah, so many flowers, trees. Yeah, I read in there and I play there and talking with my friends there. Yes, and also the campus is really very, very big. So this is a deep impression for me. Yeah, and yeah, also how to say the building is really very good, and also I have a lot of friends because I think I think this is the most the study there for me is I think is the most important foundation for my academic career. Yeah.
Okay, super. So, Paul and Elaine, I don't know whether you've gone to that campus, before or not. Actually, HUST is one of the biggest campus, in China, like a rainforest. Yeah, like Gang say that every summer is a really heavy rain, like a rainforest. So all kind of wild animals there. So I once on my way, go to the office, I met a snake on the street. So it's quite strange. Yeah, but it's very good. Memories and a lot of people there. So Chen Rong, can you tell us something about this year for the 30 years anniversary and anything to cheer up everyone?
Yeah, thank you very much. Thank you, Alice. Thank you, Gang, Professor Chen. Yeah, we really appreciate your efforts really to participate in the iCANX Summit and show you like the happy birthday on the first slide. Really, thank you very much. I mean, as an outstanding alumni of HUST, especially thank you for your contributions. And just as you mentioned that you spent 9 years at HUST, and I remember like when we read your bio, you start your undergraduate, but you were very young, right? You were like 16 or something as an undergrad student. So
I was not the youngest.
Not the youngest, but one of the youngest.
At the time, this age is more or less common. So I feel older.
Yeah, but that's actually one of the best life period there. Like right now, I mean, usually during this kind of period of time, we have a lot of trees, just as Alice mentioned, we call like forest campus. So it's green and we have a lot of trees and we have like 4 seasons in Wuhan, just as almost everybody knows here, right? We have like 4 very distinct seasons here. But what I want to really say is that for HUST is not only we have a forest, we have mountains, and we have the highest point, the highest elevations in the cities, and we also have a lakes. Right now we have this kind of such as like Harvard and MIT, you do all these boating. So we have the dragon boat teams in HUST as well. So we really welcome you back when time is possible in the future. But now I think the celebration of the 70th years anniversaries online is a great thing to have you all here. Thank you.
Okay, very nice. I think, thank all of you. And as this very special moment, because this time we host the iCANX Summit, actually we originally host in Wuhan, in the campus of HUST. So, but for the COVID-19 come back again, so we have to stay on site. So yeah, but we also have a good time. We are so proud of to have all of you here and to enjoy, this special moment. And thanks. I think that's the end of our iCANX Summit. I definitely love this. And Lan and Paul, I think next year we should continue, to have this event. We got people to go together. Yeah, that will be very nice.
Yes.
for every year the peoples can, not only science, also friendship, right? Yeah. So that's the life. Yeah. Okay. Yeah. Thank you. I hope to see you soon.
Thank
Okay.
you.
Yeah.
Thank
bye.
you.
Thank you very much.
Good to
Yeah.
see you
Bye.
all.
See you guys.
Thanks for
Yeah,
Bye.
I hope we see you in gang. I hope we see you in person in Boston and elsewhere in the world soon. And
Yes, yes. Maybe I'll come to UCLA in the summer.
oh please, we would love
Yeah,
that.
yeah. I think
Thank you.
I'll
We're
probably
so
drop
glad
by
to
there.
have you
Here's a
back.
certification for you. I will send to you. Okay. Yeah. For
Thank
my
you.
cats. Yeah.
Okay.
Okay.
Bye.
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 Yeah.
Bye.
Okay. Yeah. See you next year.